Yesterday, we looked over the formula for determining 24-hour visibility. How do we know if something will be above our horizon for 24 hours? The day before that, we looked into how to determining celestial declination. How do we manually know a sky coordinate of an object so that we can use that to determine where it'll be in other locations anywhere around the world? So you'll want to check out those two videos if you're just tuning in now. Today, we're going to look at dome refraction, what actually happens when light shines through a firmament. What we're talking about, though, what we're trying to model out is December, the 24-hour sun. We know that in December, there'll be a declination of negative 23 degrees. We showed you how to determine that yourself in the last video. So we know the sun, as it travels around the Tropic of Capricorn, that's what that purple circle is. It goes between negative 23 degrees latitude over to the other side of negative 23 because it's doing that circle. So remember, there's a one-to-one mapping up here. Celestial declination is a sky coordinate, and it maps with the one-to-one ratio. For any celestial object, there's something called the ground position. I also call it the zenith. But it has a latitude equal to the declination. Now, in this example here, there's an observer at 80 degrees south latitude. We also have an observer at 67 south latitude. I put them on opposite sides, but they're actually like right next to each other because the sun's going around, so I wanted to make the example more easy to understand. But for Union Glacier, right here, what's going to happen is when you're facing north, so I'm going to go on this side just to make it a little bit easier to explain. When you're facing north, looking at the sun, that makes perfect sense. Where people get confused, and it is understandably confusing, the sun is now going to be here. My back is to the sun. I'm looking at the dome firmament, and I still see that exact same sun, even though it's behind me. What happens is there's something called total internal reflection. What happens is when the sun first enters, it stays trapped between the gradient refractive indexes. And what that does is it captures 100% of the light. So we're not going to see it fainting. It's going to look exactly the same. That's why the photon, like the exact same sun that you would expect to see, is what we see. So it stays trapped in here, and as you see, it would just pop out. So this sun here is what this diagram is showing for the B view. When the sun is here, you're looking at the firmament that way to see it. Does that make perfect sense? Now, the example might make more sense if we go to negative 67 latitude. So that would be if we're in Union Glacier and we go north by about 13 degrees. Well, what happens, though, is you see that internal reflection, it misses the observer. What happens is the observer, when you're at there, you can only see the sun facing north. Eventually, it disappears out of your perspective. And you can model this yourself to see, go on Stellarium and check it. When you're looking at the sun, facing north to the sun, right here, you can see it. But the reason you cannot see it now that your back is to it. So in this example, it's the sun over there, and the observer is looking up at the firmament, but you can't see it because you're not close enough to it for the refraction to occur. So the formula for determining will dome fraction recur, it's a very simple yes or no. What we do is that formula, so the latitude, the absolute latitude, is it greater than 90 degrees, subtract the declination. So in this case, for the observer at negative 67, the answer is false. So 67 greater than 90, subtract 23. 67 is not greater than 67, so the answer is false. And it's true, there's no 24-hour sun there. However, over here, the formula 80 greater than 90 subtract 23, 80 greater than 67. Yeah, 80 is, so that's true. So that is how we know dome refraction occurs. And you can see actually how this relationship mathematically makes sense. If you're at the North Pole and the sun's here, you're nowhere near the dome. It's not even possible for it to refract. And it's also not even within your perspective. So see right over here, negative 23 degrees of declination. That's the sun itself. So not even refraction, just the sun itself is over there. And we have to understand that once you're too far away from it, you just can't see it. Now, think of like a fiber optic cable. That's probably the best way to describe what's happening between the gradient refractive indexes. The light is bouncing around and it pops out with a perfect signal. It's really, really interesting. So I hope that explains it. There's one other thing that's very important to understand. There is an even number of total internal reflections happening through this gradient refractive index. The reason that we know that is otherwise the sunspots wouldn't match reality. If you go to my previous videos where we looked at how the sunspots looked when in Union Glacier in the United States, Australia, we saw that it matches exactly what the flat earth model predicted. So we know that there has to be an even number of total internal reflections. So this is essentially how it all works. If you watch all the previous videos, you should have a pretty good understanding of the foundational concepts. How do we look in the sky to determine the celestial coordinate? In this case, it's negative 23 degrees of declination. This is a sky coordinate. It has nothing to do with the land. Well, it shouldn't have anything to do with the land. But you find that when you're on the globe and their model, it should not. But what we find is that on flat Earth, you have to remember, this is a sky coordinate. What we're talking about, declination, celestial declination, this is a sky coordinate that coincidentally maps perfectly to flat Earth. For example, Polaris, if you're at the North Pole looking straight up, Polaris is there. So we know this relationship holds true. So on flat Earth, declination is the location of an object on the firmament. This actually, I think, is page 49 of the Flat Earth Science textbook. Since a lot of my audience now has this, I just want to be able to mention where you would just look to reference this stuff. Did I call it? Page 26, I believe, where we talk about declination. Yeah, that's probably the introduction to it. Section 2.3 for sure. But the idea is that we know where the objects will be because it's just a parabolic dome. So if the top of the firmament is 90 degrees, let me get my protractor. This is actually the reason why we tell you guys to get a protractor from the dollar store the first time you enroll in Flat Earth University, because it makes sense. It's a flat surface. It's how the observer works. But it's also how the universe works as well. The universe is like a flat, infinite plane with the firmament, at least. We know it works like this. So 90 degrees is where Polaris is. Down at the bottom, 0 degrees. 45 would be halfway. So 45, 45. And it maps to the latitude. So if someone tells you there's a celestial object that has a celestial declination. So this is what astronomers would be using to type into their EQ mounts. A celestial declination, let's say it's at 45 degrees. Well, where is that? 45 degrees north. That would be like right there. It could be there or here. Because remember, everything travels around. Just like how for the Tropic of Cancer, it's not the small loop, it's this big purple loop here for Tropic of Capricorn. Now, I believe that covers everything. I just want to make sure that we got the formula, we got why this happens, we understand the astronomy, you understand declination. That's probably the most important thing. Make sure you understand what declination is, know how we manually determine it ourselves. That's going to be a big one. Because what globers will want to do is they want to lie to you and say that we use astronomical models, we use globe models, we use epiphemerides, VSUP 87, but that's not true. The 24-hour sun and the 24-hour moon on flat Earth, the celestial declination for those calculations are determined by first-hand observations. Anyone in the world last year on December could have determined this and predicted this. Make sure you understand that.